Today we're going to talk about something called colligative properties. Now we've been talking about solution chemistry for the past several videos, and today I want to address a property of solutions, and that's called a colligative property. You've never heard of that before, probably. You've heard of physical properties, you've heard of chemical properties, but certainly never colligative properties. So let me give you a definition, then I'm going to give you some examples, and we're going to talk about one or two of those examples on the video today. So first of all, let's define a colligative property. A colligative property is simply a property of a solution that is determined by the solution concentration not the type of the solution. So it's determined by how concentrated the solution is. Remember in the last video we talked about something called molarity, which described the concentration of a solution as being either concentrated or dilute. Well, a colligative property is a property of a solution that's determined by how concentrated that solution is, not the type of the solution, not necessarily the solute and the solvent. It's how concentrated that solution is. Now, there are four colligative properties we will discuss. Number one, vapor pressure lowering. Now, you might recall we've discussed vapor pressure before. Vapor pressure itself is not the colligative property. Vapor pressure lowering is the colligative property. I'll explain that in a few minutes. Number two, boiling point elevation. Now we've also talked about boiling point, haven't we? Boiling point is not a colligative property, but the elevation of the boiling point is. It's a property of a solution determined by how concentrated or how dilute that solution is. Number three, freezing point depression. So freezing point we've talked about before. Freezing point, kiddos, is not a colligative property. Freezing point depression is. And four, osmotic pressure. Now, we've never talked about that before. That'll be the last colligative property we discuss, and that'll be in a later video. You've probably heard of osmotic pressure if you've had a biology class. We're going to learn what osmotic pressure is in this unit, or this part of the unit, and we'll be able to apply it to the term colligative property, I hope. Alrighty? So let's start our discussion of colligative properties by describing what vapor pressure lowering is. You ready? All right. Now, on the top of the next page, I have a picture of a beaker. So, this is a beaker of pure water. Dumb question time. What is on the surface of the liquid? Yes, if you said water molecules, you are correct. It's a beaker of water, for crying out loud. So on the surface of the liquid, there are water molecules. Now, these can evaporate and create what is called vapor pressure. Let me draw a silly picture for you, okay? This beaker's on a desktop. Okay, and let's put a dome over this beaker. All right, now, on the surface of the liquid, aren't water molecules evaporating? Aren't they leaving the surface if they have enough kinetic energy? And we end up having, once again, you can't see the water molecules, but we have some water vapor in our container. Now, aren't those water molecules moving around, slamming into the walls of the container and exerting a pressure? Yeah, so I'm going to say the water inside that dome is exerting a force on the walls of that container. We call that vapor pressure. And vapor pressure is affected by temperature. As temperature increases, of course, the water molecules are going to be moving faster, and they're going to slam into the walls of that container with more force, so the vapor pressure would increase. Now, at room temperature, the vapor pressure of water is pretty close to what we call 23 millimeters of mercury. Now, air pressure on a typical day at sea level, now not vapor pressure of water, but the pressure of the air, is about 760 millimeters of mercury. So the vapor pressure of the water is 23 millimeters of mercury at room temperature. Air pressure is about 760 millimeters of mercury. So let's just fill that blank in here. At room temperature, the vapor pressure of water is about 23 millimeters of mercury. When water is heated to boiling, that's at sea level and 100 degrees Celsius, the vapor pressure of the water will end up being, as you recall the definition of boiling point, the same as the atmospheric pressure, which is 760 millimeters of mercury. So, the vapor pressure of water at room temperature is about 23. If I heat it up to 100 degrees Celsius, because remember, vapor pressure changes with temperature. It's proportional to the temperature of the liquid. And so if I were able to heat that liquid up to 100 degrees Celsius, the vapor pressure would equal atmospheric pressure, which is 760 millimeters of mercury. All right, now let's continue this discussion by looking at another picture. I'm not going to leave the first one, we'll come back to it. Now, this beaker is 10% sugar. So 10% of the particles in that solution are sugar molecules. The rest of it's water. So, dumb question again, what is on the surface of the liquid this time? Okay, very good. There's water molecules on the surface. Good. And what else is there now? Yeah, there are sugar molecules and water molecules on the surface. What do you think happens to the vapor pressure of water when I have 10% of the molecules being sugar instead of 100% of the molecules being water? Let's draw our picture again. Put this on a desktop. Put a dome over the top, right? So there are water molecules on the surface. So they're leaving the surface if they have enough energy. But what else is on the surface now? That's right. 10% of the molecules are sugar. Aren't they getting in the way of having more water molecules on the surface? 10% of them are sugar now. So can as many water molecules leave the surface and become a vapor? They can't. So the vapor pressure of the solution will be lower. Guess how much lower? That's right. It will be 10% lower. Because 10% of the molecules on the surface of the liquid are now sugar instead of water. So the vapor pressure will no longer be 23 millimeters of mercury at room temperature. And when I heat it up to 100 degrees Celsius, the vapor pressure of water, or that solution, will no longer be 760 millimeters of mercury. Those will both be 10% lower. So at room temperature, the new vapor pressure will be about 10% lower, which will be about 2.3 millimeters of mercury lower. Remember, because the vapor pressure of water at room temperature was 23, but now that 10% of it is sugar, it will be 10% lower, which is 2.3 millimeters of mercury lower. So I've just effectively lowered the vapor pressure by adding a solute to my solvent. This is a colligative property called vapor pressure lowering. Now, what effect will that have on the boiling point? See, if my vapor pressure was 23 millimeters of mercury, right, and I just lowered it by 2.3 millimeters of mercury, isn't the vapor pressure of the solution now going to be about 20.7 millimeters of mercury? What effect will that have on the boiling point of the solution? Well, let's see. When this solution is heated to 100 degrees Celsius, the new vapor pressure, once again, will be about 10% lower, which at 100 degrees will be about 76 millimeters lower. And so it will go down to 684 millimeters of mercury. Remember, 760 is the vapor pressure of pure water at 100 degrees Celsius. If it's lowered by 10%, 76 millimeters of mercury, doesn't that give us 684 millimeters of mercury now? Yeah, the vapor pressure is quite a bit lower. Question, will the solution boil at this temperature? It won't. Remember, because boiling point is defined as the temperature when the vapor pressure of the liquid equals atmospheric pressure, which is typically 760. So the vapor pressure of the solution is lower than 760. Remember, it's only 684? So how do we get it to boil? Yeah, it's not hot enough yet, is it? So the solution right now at 100 degrees Celsius will not boil. What do we need to get that solution to boil? Well, we need to increase the solution's temperature. This is a colligative property called, you ready for it? Boiling point. Remember, we just had to increase that temperature, so it's called boiling point elevation. So, because the vapor pressure is lower, the boiling point is higher. It turns out it doesn't matter if the solute is sugar or something else. So long as 10% of the solution is made of solute particles, both the vapor pressure lowering and the boiling point elevation will be the same. All right, we'll talk more about this and identify a couple other colligative properties in our next video. See you soon. Bye-bye.